Ehe. May 5, 1943, Nibelungenwerk Factory, St. Valentin, Austria. A Soviet T-34 tank is burning in a test field, 300 meters away. Hit from a weapon so powerful that the armor didn't just crack, it evaporated. The crew inside never had time to scream. The shell traveled faster than the sound of the gun that fired it. By the time anyone heard the explosion, the tank was already dead. The men watching this test said nothing for almost 10 seconds. Then, one of them, a senior Wehrmacht officer with 30 years of military experience, turned to the engineer beside him and said 4 words. "We cannot stop this." He wasn't talking about the Soviet tank. He was talking about the weapon that killed it. In the spring of 1943, while Germany was losing the war on 3 fronts simultaneously, while Allied bombers were turning the Ruhr industrial heartland into burning rubble every night, while copper was being stripped from church bells and telephone lines just to keep ammunition factories running, German engineers at a small factory in the Austrian town of St. Valentin were building something that had no right to exist. 91 machines, each one weighing 65 tons, each one powered by a hybrid electric propulsion system. The kind of technology most nations wouldn't attempt for another 30 years. Each one carrying 200 millimeters of frontal armor that no Allied weapon in widespread service could penetrate. Each one armed with a gun so precise it could destroy any tank on Earth at 2 kilometers with the first shot. This is the story of the Ferdinand. And nothing about its existence makes sense. By January 1943, Germany's strategic situation had turned from difficult to catastrophic. Stalingrad had fallen. Field Marshal Paulus surrendered 300,000 men. The myth of German invincibility on the Eastern Front, the myth that had sustained morale for 2 years, lay in frozen ruins on the banks of the Volga, dead. The scale of what happened at Stalingrad went beyond military defeat. It was industrial murder. Germany lost not just soldiers but tanks, artillery pieces, trucks, engineering equipment, aircraft, and entire armies' worth of equipment that the factories back home were increasingly unable to replace. Every Panzer III sent to the Eastern Front required machine tools, skilled welders, ball bearings, rubber seals, copper wiring, manganese, steel. All of these were already in short supply before Stalingrad. After it, the shortage became a crisis. At the same time, the Casablanca Conference in January 1943 formalized what had already been happening in the skies over Germany. Roosevelt and Churchill agreed to commit fully to the progressive destruction of the German military-industrial system. Not raids. Not disruption. Systematic destruction. British Lancaster bombers hammered German cities at night in massive formations. American B-17 hit specific industrial targets during the day, attempting to surgically remove the machinery that kept German forces fighting. The Ruhr Valley, Germany's industrial heartland, was burning. Steel mills that fed the tank factories were interrupted, damaged, forced to reduce output. Rail networks that moved raw materials and finished components became targets. A crankshaft manufactured in Essen might now sit in a bombed-out freight yard for 3 weeks before reaching an assembly line in Berlin. A precision ball bearing from Schweinfurt might never arrive at all. The German army facing the Soviets across hundreds of kilometers of frozen steppe needed more tanks, better tanks, tanks that could survive Soviet anti-tank guns, tanks that could destroy Soviet armor at ranges that kept German crews alive. What Germany was getting instead was production delays, material shortages, and factories operating at 2/3 capacity, while engineers adapted designs on the fly to work around missing components. Soviet armor was improving fast. The T-34 had already shocked German tank crews in 1941. Its sloped armor-wide tracks and powerful gun had been a genuine revelation to men who expected to face inferior Soviet equipment. By 1943, the T-34 was being produced in quantities that defied comprehension. Factories beyond the Ural Mountains that Luftwaffe bombers couldn't reach were pouring them out in thousands. The KV-1 heavy tank had frontal armor that early German anti-tank guns simply couldn't penetrate. And intelligence reports were describing something new coming: heavier tanks, better armed, More protection. Germany needed an answer. Not eventually. Now. The answer had almost been discarded entirely before the war even reached its critical turning point. And the man whose name the answer would carry had already been told no. Ferdinand Porsche was not a military man. He was an engineer. Born in 1875 in what is now the Czech Republic, he had spent his entire adult life thinking about machines. Not weapons. Machines. Engines, transmissions, the relationship between mechanical force and motion. By the time World War II began, he was arguably the most celebrated automotive engineer in Europe, the man whose small company had produced the Volkswagen, the people's car, from Hitler's personal directive. And this relationship with Hitler was not incidental. It was central to everything that followed. Porsche had access that most engineers, most generals even could never achieve. When he had an idea, he could get it heard at the highest levels of the German state. And in 1941, Ferdinand Porsche had an idea that his colleagues considered completely insane. Conventional tank transmissions of the era were brutally mechanical. Gears ground against gears. Clutches absorbed tremendous friction while braking one track to execute turns. The components wore out constantly. In the extreme cold of Russia, transmission fluid-thickened gears seized vehicles that had functioned perfectly in German summer became useless in Soviet winter. Mechanical transmissions were the single most common cause of German tank breakdowns on the Eastern Front, a fact that filled maintenance reports and frustrated commanders who found themselves with theoretically functional tanks that simply refused to work. Porsche's solution was to eliminate the mechanical transmission entirely, replace it with electricity. 2 engines in the rear hull. Not to drive the tracks directly, but to power generators. Those generators would produce electrical current. That current would flow to electric motors, one for each track. The motors would drive the tracks. Steering the tank would require no clutches, no braking, no mechanical stress. The driver would simply vary the electrical current to each motor. More power to the left motor. The tank curves right. Equal power reversed to both motors. The tank rotates in place, a 65-ton machine turning like a dancer on its own axis. His colleagues told him this was madness. Germany was already short of copper. Electric motors required copper wire wound in precise coils around iron cores. Generators required the same. 4 precision electrical machines per tank, each consuming copper that the Reich was melting church bells to find. Building hybrid electric tanks during a copper famine wasn't bold engineering. It was in the view of the Armaments Ministry borderline criminal waste. The competing design came from Henschel, simpler, more conventional, a standard mechanical transmission using components already in the supply chain, assembled by workers already trained in existing processes. When evaluations concluded in 1942, the Armaments Ministry chose Henschel, the practical choice, the sensible choice. Porsche had already ordered production of 100 chassis. This is the moment where the Ferdinand story becomes something other than a straightforward engineering history. Because Porsche's confidence in his own design had led him to begin manufacturing before the competition concluded. By the time the decision came down in favor of Henschel, the Nibelungenwerk factory in St. Valentin had already produced a substantial number of Porsche Tiger chassis, running gear assembled, electric drive systems in place. Hulls built to specifications that the winning design had made irrelevant. Scrapping them was unthinkable. The steel alone represented weeks of production from mills now operating under constant threat of air attack. The electrical components, the generators, the motors, the control systems represented copper that had been fought over in allocation committees for months. You don't destroy that. Not in 1943. Not when every gram of material had been extracted from a system already operating beyond its limits. On May 18, 1942, Albert Speer's Ministry for Arms and Armament issued an order: develop a self-propelled anti-tank vehicle using the existing Porsche chassis. The hulls would not be wasted. They would be transformed. An armored superstructure would be built atop each hull. Inside it, Germany's most powerful anti-tank gun would be mounted. The vehicle would not be a tank. It would be something more specialized, more lethal at its specific purpose, and more heavily protected than anything else on the battlefield. It would be named the Ferdinand after the man who had created its foundation. The engineering challenge this presented was extraordinary. The Porsche chassis had been designed around specific weight distributions for a tank configuration, a turret-mounted weapon that would balance differently than a fixed rear superstructure. Adding the superstructure changed everything. The weight distribution, the suspension loads, the cooling requirements for engines now working harder to move additional mass. Each modification created 3 new problems to solve. The original air-cooled engines Porsche had specified were replaced with Maybach HL 120TRM water-cooled units, the same engines powering Panzer III and IV tanks. This was pragmatic. Spare parts existed, mechanics knew them, but replacing the engines required redesigning the rear hull's cooling systems, the mounting arrangements, the exhaust routing. In a peacetime factory with unlimited time and resources, this would have been a significant engineering project. In St. Valentin in 1943, it was one of 100 simultaneous crises that the engineering team navigated without losing the production schedule. The weapon mounted in the Ferdinand superstructure was the 8.8 centimeter PaK 43/2L/71. The designation L/71 meant the barrel was 71 times the diameter of the bore in length. 71 times 88 millimeters. A barrel more than 6 meters long, machined from hardened steel to tolerances measured in fractions of a millimeter across every centimeter of that length. Any deviation from perfect straightness across 6 meters of steel would send rounds flying off target. At the engagement ranges, the Ferdinand was designed to fight 1 to 2 kilometers. Even tiny manufacturing imperfections translated to catastrophic inaccuracy. The gun had to be perfect. Not acceptable. Not within reasonable tolerance. Perfect. This barrel fired armor-piercing rounds at velocities exceeding 1,000 meters per second. Faster than most rifle bullets. At those velocities, trajectory at combat ranges was essentially flat. The round traveled almost in a straight line from gun to target, simplifying the calculations a gunner needed to make, and enabling first-round hits that shorter-barreled weapons simply could not achieve. A T-34 at 1,500 meters was not a challenge. It was a certainty. Mounting this gun in a fixed superstructure rather than a rotating turret was a deliberate design choice. A turret capable of holding this weapon armored to the standards the Ferdinand required would have been mechanically impossible given the vehicle's total weight. The fixed mount limited traverse to a few degrees left or right. Aiming required moving the entire vehicle. Critics called this a fundamental tactical flaw. The engineers called it the only option. The frontal armor protecting the crew was 200 millimeters thick. In a world where the T-34 had 45 millimeters, where the American Sherman had 50, where even the feared Tiger I had 100, the Ferdinand had 200. No anti-tank weapon in widespread Allied service during 1943 could penetrate that plate from the front at practical combat range. Soviet gunners would fire. Rounds would bounce. The Ferdinand would keep coming. Producing this armor required steel that Germany was struggling to make in adequate quantities. The alloys that gave armor plate its critical combination of hardness and toughness, manganese, nickel, molybdenum, were all in short supply. The welding of plates this thick demanded equipment operating at sustained high temperatures, skilled operators who knew exactly how to lay each weld bead to avoid creating stress fractures, and time that production schedules increasingly refused to provide. They built 91 of them. In 1943, while Allied bombers hit the Ruhr every night, while copper was being stripped from telephone lines, while skilled workers were being conscripted to replace the men dying on the Eastern Front. But by the early summer of 1943, the Ferdinands were ready. Not perfect, no weapon system is ever truly finished when it enters combat, but functional. Armed. Armored. Moving on their electric drives with a smoothness that shocked test observers. The crews assigned to them had gone through training that couldn't fully prepare them for what these machines were capable of, because nothing quite like them had ever existed before. In June 1943, they were loaded onto rail transport and sent east, specifically to a section of the Eastern Front, near a small Soviet city that would give its name to the largest armored battle in human history. Kursk. And the German plan was to cut off a massive Soviet salient, a bulge in the front line, with simultaneous attacks from the north and south. The Ferdinands were assigned to the northern pincer, tasked with breaking through Soviet defensive lines that intelligence reported were extraordinarily deep and heavily prepared. Minefields, anti-tank ditches, artillery positions, fortifications built specifically to stop the German armor that Soviet intelligence had told Stalin was coming. What neither side fully understood in those final days before the offensive was how completely each had misread the other's capabilities. The Soviets thought they knew how to stop German tanks. The Germans thought they had brought something the Soviets had never seen. They were both right, and both catastrophically wrong. The Ferdinand's electric motors hummed in the pre-dawn darkness of July 4th, 1943. 90 machines, their 88mm guns loaded, their crews cramped inside armored boxes moving on technology that belonged to a different decade. Ahead of them, the most heavily defended ground in the world. In Part 2, we witness what happened when the most sophisticated armored vehicle ever built met an enemy that had prepared for exactly this moment, and discover why the Ferdinand's greatest threat wasn't the Soviet guns waiting in front of it, but something far smaller, far closer, and far more terrifying than anything Ferdinand Porsche had ever considered when he drew his first blueprint. 91 hybrid electric tank destroyers, built during a copper famine, armed with guns that could kill anything on Earth at 2 kilometers, armored so heavily that Soviet gunners could fire until they ran out of shells and accomplished nothing. In Part 1, we watched Ferdinand Porsche's rejected vision become the most formidable anti-tank weapon Germany had ever fielded. We watched the machines roll off the production line at St. Valentin, while Allied bombers turned the Ruhr to rubble. We ended on the edge of Kursk, the largest tank battle in human history, with 90 Ferdinands humming in the darkness waiting for dawn. Here is what the German High Command did not know on the morning of July 4th, 1943. The Soviets had been preparing for this exact attack for 4 months. Not guessing, not estimating, knowing. Soviet intelligence had penetrated German operational planning at the highest levels. Marshal Zhukov had told Stalin in April that the Germans would attack the Kursk salient from the north and south simultaneously, with their heaviest armor leading. Stalin had listened. And for 4 months, 300,000 Soviet soldiers had done nothing but dig. What waited for the Ferdinands wasn't a defensive line. It was a killing system. General Walter Model commanded the northern pincer. He was not a man who welcomed doubt. 52 years old, decorated from the First World War survivor of the Eastern Front's worst winters model, had built his reputation on aggressive action and iron discipline. When his staff officers presented intelligence reports about Soviet defensive density in the Ferdinand's operational sector, he looked at the numbers and made a decision that would echo through military history. He decided the Ferdinands would handle it. The briefing on July 3rd should have been a warning. Soviet engineers had laid approximately 2,400 anti-tank mines per kilometer of front in the Ferdinand's attack sector. Anti-tank ditches 3 meters deep cut across the approaches. Artillery positions were pre-registered on every natural approach route. And behind all of it, Soviet anti-tank gun regiments equipped with the 76mm ZIS-3A weapon that couldn't penetrate the Ferdinand's front, but could absolutely destroy its running gear, its vision ports, its gun barrel. One of Model's staff officers, a lieutenant colonel named Reinhardt, who had studied the Ferdinand specifications, carefully raised his hand during the briefing. "Herr General, the Ferdinand has no hull machine gun. Infantry will be able to approach from the flanks once we're through the first defensive belt." Model stared at him for a moment. "The Ferdinand will not be fighting alone. Infantry will provide close protection." The terrain in the second defensive belt. The Ferdinand's gun will suppress the anti-tank positions before infantry engagement becomes necessary. This discussion is concluded. It wasn't concluded. But Reinhardt understood that in Model's headquarters it was. The next morning the Ferdinands moved forward into history, and into a trap that no amount of frontal armor could solve. The first hours were everything the designers had promised. Operating at 1,500 to 2,000 meters, the 88mm PaK-43 guns fired with devastating precision. T-34s positioned in hull-down fighting positions dug in, so only their turrets showed, disappeared in fireballs. Soviet anti-tank gun positions that had taken weeks to construct were reduced to scrap metal in seconds. The crews of Ferdinand 313 reported destroying 11 Soviet vehicles before noon. Ferdinand 221 cleared an entire anti-tank gun battery at 1,800 meters in 4 shots. The Soviet defenders tried everything they knew. Direct fire from 76mm guns against the Ferdinand's fronts accomplished nothing. The rounds hit and bounced. Soviet commanders watching through periscopes saw their best anti-tank weapons fail completely. The 200mm plate held. Round after round after round, and the Ferdinands kept coming. For approximately 4 hours, it looked like the critics were wrong. Then the Ferdinands entered the second Soviet defensive belt. The terrain changed. The open steppe gave way to ground that had been deliberately flooded in places, channeling the heavy vehicles onto specific routes. Those routes were mined. German engineers swept forward to clear paths, but they were working under fire, under pressure, making mistakes. 3 Ferdinands detonated mines that destroyed their running gear. They stopped. They couldn't move. And Soviet infantry materialized from the grass. Not tanks, not artillery, infantry. Men with grenades and gasoline and Molotov cocktails and determination born of fighting for their own country on their own soil. They had studied the Ferdinand schematics, captured German documents, intelligence analysis, engineer assessments, and they knew exactly where to look. The rear deck, the engine compartment ventilation, the vision ports. Monsieur. A Ferdinand without a hull machine gun is a Ferdinand that cannot engage targets closer than the gun can depress. A man crawling in dead ground 30 meters away is effectively invisible to a crew sealed inside a steel box. The crews could hear boots on the hull. They could hear the grinding sound of a magnetic mine being placed against the rear plate. They could hear everything and shoot at nothing. By nightfall on July 4th, Germany had lost 17 Ferdinands to mechanical breakdown and infantry assault. Not to anti-tank guns, not to Soviet tanks, to mines and men with grenades attacking machines that couldn't see them. General Model received the evening report in silence. The fundamental problem wasn't the Ferdinand's armor or its gun. Both performed exactly as designed. The problem was the assumption baked into its conception that it would always operate with infantry protection, always fight at long range, never find itself isolated in broken terrain, surrounded by enemies too close for its weapon to engage. Lieutenant Colonel Reinhardt had known this. He had raised it the day before the attack. He had been told the discussion was concluded. Now, with 17 machines destroyed or disabled on the first day, the discussion reopened itself whether anyone wanted it to or not. Reinhardt found himself in a command tent at 2200 hours, standing across a map table from Colonel Ernst von Jungenfeld, commanding officer of Schwer Panzerjägerabteilung 654. Jungenfeld had spent the day watching his vehicles. His crews fight their way through Soviet defensive lines while infantry picked off the ones that stopped. "We need a machine gun in the hull," Reinhardt said. Jungenfeld looked at him with the particular exhaustion of a man who has been proven right about something terrible. "I suggested that 6 months ago. I was told it would compromise the frontal armor." "It won't. The bow plate has sufficient thickness to accommodate a ball mount without structural compromise. A standard MG-34 installation, 4 days of modification work per vehicle." "We don't have 4 days." "No. But after Kursk, when this offensive concludes, whatever the result, the surviving vehicles will need it. Jungenfeld looked at the map, at the markers showing where his Ferdinands had stopped, where they'd burned, where crews had abandoned vehicles that couldn't be recovered under fire. "Write the technical specification," he said. "I'll sign it." The offensive continued for 9 more days. The results were operationally complicated and mechanically catastrophic. The Ferdinand's long-range performance remained extraordinary throughout. Their kill ratios against Soviet armor were among the highest of any German unit at Kursk. Crews reported engagement after engagement where they destroyed multiple Soviet vehicles at ranges that made return fire impossible. The gun worked. The armor worked. But the attrition mounted. Breakdowns accelerated as the vehicles pushed beyond their tested operational range. Cooling systems struggled in July temperatures that pushed engine compartment heat beyond design parameters. Recovery operations for disabled vehicles, each weighing 65 tons, required assets that simply didn't exist in adequate numbers. When a Ferdinand broke down in contested territory, the options were recover it under fire with equipment barely capable of the task, or abandon it. Many were abandoned. By the time Operation Citadel officially ended on July 23rd, German forces having failed to cut off the Kursk salient, the Ferdinand battalions had suffered losses that shocked even pessimistic observers. Of the 90 machines that had entered combat, fewer than 50 remained operational. Some had been destroyed by enemy action. More had been lost to breakdown recovery failure and the grinding mechanical stress of combat that no testing program had fully anticipated. The survivors were pulled from the line, loaded onto rail transport, sent back to St. Valentin. What happened next is either the most rational response to combat failure in German military history or the most irrational allocation of resources in a war that Germany was visibly losing. The Nibelungenwerk engineers received the surviving Ferdinands with lists of field modifications that Jungenfeld Reinhardt and surviving crew commanders had compiled through the blood and fire of Kursk. Hull machine gun. The MG-34 ball mount that Reinhardt had specified in his tent at 2200 hours on July 4th. Simple. Effective. Should have been there from the beginning. Commander's cupola. The original Ferdinand had given its commander almost no visibility while buttoned up. A new cupola with 360-degree periscopes would let him see threats approaching from any direction, including infantry crawling through dead ground. Wider tracks. The original tracks had proven inadequate for soft ground. The wider units would reduce ground pressure across the 65-ton weight. Zimmerit coating. The entire exterior covered in a paste that hardened into a textured surface, preventing magnetic mines from adhering to the hull, directly addressing the tactic that had disabled so many vehicles in the Kursk defensive belts. The modified vehicles received a new name, Elephant. 48 of them were rebuilt modified and sent to a front that suited them far better than the Kursk steppe had. Italy. The narrow mountain roads, the prepared defensive positions, the channeled terrain that prevented the flanking attacks that Soviet infantry had exploited so ruthlessly. In Italy, the Elephant's fixed gun and massive frontal armor were advantages, not liabilities. Allied tank crews attacking up the Anzio beachhead approaches found themselves being engaged at 2,000 meters by weapons their guns could not answer. Sherman tanks exploded. Crews died. The Elephant waited in prepared positions with clear fields of fire, and nothing drove it out from the front. But here is what the German High Command did not know in the autumn of 1943, as the modified Elephants were being prepared for Italy. Soviet engineers had spent the months since Kursk studying every disabled Ferdinand they had captured. They had stripped the electrical systems, analyzed the armor composition, mapped the vision port positions, and the ventilation locations, and the exact dimensions of the running gear. They had sent detailed technical reports to factories beyond the Urals, and they had begun building something specifically designed to kill it. In Part 3, we discover what the Soviets learned from the Ferdinands they captured at Kursk, and why the weapon they built in response would force German engineers into a decision so desperate, so resource-intensive, so strategically questionable, that even Albert Speer called it madness. The arms race triggered by 90 hybrid electric tank destroyers was about to consume resources on both sides that neither could afford. And the men who would pay the price weren't engineers or generals. They were the crews sealed inside steel boxes on roads in Italy and the forests of Ukraine. And one of them was about to make a decision that would save his entire platoon and cost him everything. 91 hybrid electric tank destroyers built during a copper famine. A gun that killed at 2 kilometers. Armor that bounced everything the Soviets fired at it. At Kursk, the Ferdinands proved their devastating long-range capability and revealed a fatal blind spot. Soviet infantry crawled through the grass and destroyed machines that no anti-tank gun could touch. The survivors were pulled back, rebuilt, renamed Elephant, and sent to Italy. In Part 2, we watched German engineers correct the machine's failures, and Allied tank crews in Italy discover that approaching an Elephant from the front was a death sentence. But Soviet engineers had spent 3 months studying every disabled Ferdinand they captured at Kursk. They had stripped the electrical systems down to bare wire, measured the armor plates to the millimeter, photographed the ventilation points, the vision ports, the running gear geometry. And in factories east of the Ural Mountains, they had sent the findings to men whose only job was to answer one question. How do you kill something that cannot be killed from the front? By the winter of 1943, they had an answer. And what followed would force both sides into an arms race that consumed resources neither could afford on a timeline that neither could sustain. Major General Vasily Mishin received the technical intelligence report on the Ferdinand in August 1943, 6 weeks after Kursk. He read it twice. Then he summoned his engineering staff and told them something that surprised everyone in the room. "We are not trying to defeat this vehicle's armor," he said. "We are trying to defeat its crew." The distinction was everything. Soviet analysis had identified 3 exploitable characteristics. First, the Ferdinand's vision was poor. The original cupola gave the commander almost no lateral visibility while buttoned up. Second, its minimum engagement range was approximately 400 meters because the gun could not depress enough to hit targets closer than that on flat ground. Third, its running gear, the tracks, the drive wheels. The suspension was vulnerable to artillery fragments in ways the frontal plate was not. But Soviet artillery doctrine changed accordingly. Instead of massing anti-tank guns against elephant fronts, commanders began directing fire at the tracks. Instead of frontal assault, infantry used smoke and terrain to close inside 400 meters, where the 88mm gun became geometrically useless. Artillery pre-registered on likely elephant operating positions not to penetrate the armor, but to destroy the running gear and strand the crew inside a machine they couldn't drive. The results were immediate. In the fighting around the Dnieper River crossings in September and October 1943, 3 elephants were disabled and abandoned not by anti-tank fire, but by artillery concentrations that shredded their running gear while leaving the armor intact. Soviet engineers who examined the abandoned hulls found crews who had been unable to evacuate under fire. The machines were functionally invulnerable. Their crews were not. German battalion commanders filed detailed after-action reports that reached Jungenfeld's desk in Italy and Model's headquarters on the Eastern Front simultaneously. The Soviets had adapted. They had found the edges of a weapon that didn't have many edges to find. And they were exploiting those edges with a methodical precision that reflected how seriously they took the threat. Soviet factories, meanwhile, began accelerating production of the ISU-152, a self-propelled gun mounting a 152mm howitzer, capable of destroying an elephant from the side at combat range. Not elegant, not precise, but devastating. A 152mm shell didn't need to penetrate 200mm of frontal armor if it could hit the side at 80mm. The weapon was nicknamed Zveroboy, Animal Hunter. The animal it was designed to hunt was the elephant. By the end of 1943, Soviet industry had produced over 700 ISU-152 units against 48 elephants.
남계.
The crisis those numbers represented landed on Albert Speer's desk in November 1943 as something more complicated than a simple military problem. The Elephant program had consumed extraordinary resources: copper precision machine tools, skilled engineers, factory capacity to produce 48 vehicles. Those 48 vehicles were now facing an opponent who had built 700 counters to them and was building more every month.
By.
The officer who delivered this assessment to Speer, a logistics colonel named Hartmann, did not survive the meeting professionally. Speer listened to the numbers, looked at the production projections, and asked a question that contained its own answer. Are you telling me that the Ferdinand program consumed enough copper to produce 700 ISU equivalents, and the Soviets used that resource advantage to build exactly that? Hartmann said nothing. Then the Ferdinand, Speer said carefully, may have cost us more than it contributed. Word of this assessment reached Porsche's associates through the bureaucratic networks that connected German industrial and military planning. The man whose name the vehicle carried was not summoned. He was not informed officially, but in the precise, devastating way that institutions communicate disapproval without direct confrontation. Ferdinand Porsche understood that the machine bearing his name was being reconsidered at the highest levels. The surviving elephants in Italy were performing well-kill ratios that justified their existence on an individual tactical level. But individual tactical performance wasn't the metric that mattered anymore. What mattered was the aggregate. And the aggregate said that Germany had traded resource efficiency for engineering sophistication at a ratio it could not sustain. Engineers at Nibelungenwerk, who had worked 70-hour weeks for a year to build these machines, received no official criticism. But the production orders that should have followed the Elephant program, the expansion the next generation, the improved variants that always followed a successful weapon, did not come. The Elephant would not be mass-produced. There would be no Ferdinand II. February 3, 1944, Anzio Beachhead, Italy. Road junction at Caraceto. Oberfeldwebel Klaus Brenner commanded Elephant 102 of Schwere Panzerjägerabteilung 653. He had been with the Ferdinand since Kursk. He had watched the modifications added at Nibelungenwerk. He had driven the rebuilt machine into Italy in December and spent 6 weeks learning the terrain around Anzio with the intimate knowledge that comes from knowing your survival depends on it. On February 3rd, the Allied 1st Armored Division began a push toward Caraceto Junction with the objective of breaking the stagnant beachhead lines. 42 Sherman tanks, supporting infantry, artillery preparation that began at 0430 and lasted 90 minutes. When the Shermans moved at 0600, Brenner was waiting. His Elephant sat in a prepared fighting position hull down behind a low stone wall, only the gun and upper superstructure exposed. His gunner, Unteroffizier Metz, had pre-ranged the approaches the previous day. Every terrain feature had a number. Stone wall at right 1,400 meters. Road junction center 1,800 meters. Farm building left 1,100 meters. The first Sherman appeared at 0612. Metz said one word, ready. Brenner said fire. The 88mm PaK-43 spoke. The round traveled 1,400 meters in 1.4 seconds. The Sherman stopped. It didn't explode immediately. The round had punched through the frontal armor and killed the crew before any secondary fire began. It simply stopped moving and began burning from the inside out. The second Sherman saw the first burning and accelerated. Faster was not safer. Metz adjusted 4 degrees left. Fire. The round hit at the turret ring. The turret lifted off the hull and landed 15 meters away. The hull burned, and the third and fourth Shermans attempted to use the burning vehicles as cover angling to use smoke. Smart tactics, not smart enough. Metz tracked through the smoke on sound and on the heat shimmer visible through his sight. The third round hit the third Sherman at the drive sprocket, not a kill shot, but it threw the track, and the tank slewed sideways and stopped broadside to Brenner's position. Brenner told Metz to use it as a ranging marker. The fourth Sherman crossed behind it, and Metz took it through the thinner side armor at 800 meters. 4 shots. 4 Shermans. 9 minutes. The Allied company commander radioed back heavy anti-tank fire type, unknown accurate beyond expected range. He requested artillery. He requested smoke. He did not request additional armor, because he had already understood that sending more Shermans forward was sending more men to die. The artillery came at 0640, 14 minutes of 105mm fire that saturated the area around Brenner's position. 3 rounds landed within 10 meters of the Elephant. Fragments struck the hull. The Zimmerit coating held against magnetic mines, but it wasn't designed for artillery fragments. 2 impact marks appeared on the side plate, neither penetrating the 80mm side armor at those oblique angles. When the artillery lifted, Brenner moved. 300 meters left into a second prepared position his crew had dug the previous week. Military discipline: never stay where you were after taking fire. The 5th Sherman, advancing cautiously through the smoke of the artillery barrage to assess the situation, found the original Elephant position empty. Its commander was scanning the terrain with binoculars when Metz fired from the new position at 1,600 meters. 5th Sherman, 11 minutes total. The Allied push toward Carocheto stalled. 3 other German defensive positions contributed to stopping the advance, but the after-action report submitted by the Allied 1st Armored Division identified Elephant 102's position as the primary obstacle. The attack was redesigned to avoid the sector Brenner's machine dominated. A single crew in a single machine had forced a division-level tactical change. The February fighting around Anzio produced numbers that landed in both German and Allied operational analysis with different implications. Elephant 102 alone was credited with 11 vehicle kills during the month of February. Sherman tanks, armored cars, 1 self-propelled gun that had attempted to engage at 900 meters and discovered that 900 meters was well within the PaK 43's effective range. Across the Anzio sector, the 8 operational Elephants of Abteilung 653 were credited with 47 Allied armored vehicle kills during February and March 1944. Allied tank commanders adapted by simply refusing to engage in terrain where Elephants held prepared positions. They routed around. They waited for air support. They changed the geometry of their attacks to avoid corridors where the 88mm gun could operate at its designed range. And this was, in purely military terms, a strategic success. 8 vehicles had altered how an entire Allied armored division fought in a 40-kilometer sector. But the German sides of the ledger told a different story. Of the 8 operational Elephants in February, 5 remained operational in April. 2 had broken down in positions that couldn't be recovered under Allied artillery and air pressure. Spare parts were increasingly difficult to obtain. The precision electrical components, the generators, the traction motors, the control systems required. Specialized manufacturing that competing demands had made nearly impossible to supply to Italy. Brenner filed a maintenance report in March, noting that Elephant 102's right traction motor was showing irregular power output. He requested replacement parts. The request went up the chain. It came back 3 weeks later, parts unavailable, no production timeline confirmed. He kept driving with the degraded motor. You worked with what you had. By the spring of 1944, the Ferdinand story had acquired a shape that military historians would spend decades analyzing. A weapon of extraordinary individual effectiveness deployed in insufficient numbers to alter strategic outcomes. Kill ratios that justified every resource decision made by the engineers at Nibelungenwerk. An overall impact on the war's trajectory that fell far short of what those kill ratios might suggest was possible. The ISU-152 units the Soviets had built specifically to counter the Ferdinand were encountering the modified Elephants in Italy and finding that the tactical problem Mission's engineers had identified side armor running gear, vulnerability vision limitations had been partially addressed by the Nibelungenwerk modifications, but not eliminated. The cupola helped. The wider tracks helped. The Zimmerit helped. Nothing changed the fundamental arithmetic of 48 vehicles against 700. On the Eastern Front, Soviet armored doctrine had evolved so completely in response to the Ferdinand's capabilities that the changes outlasted the vehicles themselves. Tactics developed to defeat the Ferdinand combined arms coordination, artillery targeting of running gear, close infantry armor integration became standard Soviet practice that proved effective against every subsequent German heavy vehicle. The Ferdinand had changed how armies fought, not just against it, but in general. That legacy was invisible to the men living it. To Brenner, it was a degraded right traction motor and no parts available. To the engineers at Nibelungenwerk, it was production orders that had not arrived. To Porsche, it was silence from the ministry that had once celebrated his vision. But here is the question that Part 4 will answer, the question that the kill ratios and the production statistics and the after-action reports cannot address on their own. What happens to an idea when the machines that carried it are gone? The last operational elephants were destroyed or captured in 1945. The factories that built them were occupied or bombed into rubble. The engineers who solved the unsolvable problems of 1943 scattered across a defeated country. Ferdinand Porsche himself would face a war crimes tribunal before the decade ended. And yet the technology they built, hybrid electric drive, neutral steering, electrical power distribution between independently driven tracks, would reappear in military vehicles decades later. In civilian vehicles. In the machines you drive today. The story of the Ferdinand is not over when the last one burns. It is just beginning to become something else entirely. Something its creators never intended and never lived to see. The final chapter of this story isn't about what the Ferdinand destroyed. It's about what it built in the minds of engineers who studied it long after the war ended, in armies that learned from both its brilliance and its failures, and in a technological legacy that traveled from a burning test field in Austria in 1943 to roads and battlefields that Ferdinand Porsche never imagined. That chapter, the one most historians never reach, is what Part 4 is for. From a rejected tank design to 91 hybrid electric killing machines built during a copper famine. From Porsche's humiliation at the armaments ministry to Kursk, where the Ferdinands proved devastating at range and catastrophically vulnerable up close. From the modifications at Nibelungenwerk to the killing fields of Anzio, where 8 elephants forced a division-level tactical change. In 3 parts, we watched German engineers achieve what should have been impossible, watched the machines they built succeed brilliantly and fail fatally, and watched both sides adapt to a weapon that shouldn't have existed. Part 3 ended with a question. What happens to an idea when the machines that carried it are gone? The answer is stranger, more tragic, and more consequential than anything the engineers at St. Valentin could have imagined in 1943. Because the Ferdinand story does not end with the last burning hull in 1945. It ends somewhere you would never think to look, and the man whose name the machine carried spent his final years in circumstances that tell you everything about the distance between engineering greatness and historical justice. Ferdinand Porsche survived the war. That fact alone sets him apart from many of the men who built and crewed the machines bearing his name. He was 70 years old when Germany surrendered in May 1945. He had spent the war years designing vehicles, the Volkswagen, the Tiger tank competitor, the Ferdinand, numerous other projects that competed for ministry attention, with varying results. He had operated at the highest levels of the Nazi war economy, with access to Hitler that most generals envied, and a public profile that made him one of the most celebrated engineers in Europe. In August 1945, French authorities arrested him. The charge was war crimes, specifically the use of forced labor at Volkswagen factories during the war, where concentration camp prisoners and foreign workers had been used under conditions that killed an unknown number of them. Porsche spent 20 months in French custody. He was never formally tried. The evidence against him personally, as distinct from the system he operated within, was considered insufficient for prosecution. He was released in August 1947 after his son Ferry paid a substantial sum that the French characterized as legal fees, and that most historians characterize as a ransom. He returned to Stuttgart. He was 72 years old. His company, which Ferry had kept operational during his imprisonment, was producing the first Porsche sports cars, the 356, built partly from Volkswagen components, the beginning of a lineage that would make the Porsche name synonymous with automotive performance rather than wartime engineering. Ferdinand Porsche never spoke extensively about the Ferdinand tank destroyer in his remaining years. He gave interviews about the Volkswagen, about automotive design philosophy, about his early career. The tank bearing his name received little mention. Whether this reflected genuine disinterest, deliberate avoidance of wartime associations, or simply the forward-looking focus of an engineer who always cared more about the next problem than the last one, is impossible to determine from the historical record. He died in January 1951, 6 years after the war ended, a stroke followed by complications. He was 75. The Porsche 356 was already in limited production. The company that would eventually build some of the most successful racing and sports cars in history was operational and viable. He died knowing that the name he had spent his life building would survive him, but almost certainly not knowing in what form it would survive, or how completely it would be separated in public memory from the tank destroyer that bore his name in 1943. The men who had told him his electric drive was insane, the armaments ministry officials who had chosen Henschel, the officers who had questioned the copper allocation, the engineers who had called the design impractical, most of them faced fates ranging from imprisonment to obscurity. Albert Speer, who had overseen the entire German armament system, including the Ferdinand program, served 20 years in Spandau prison and died in 1981. The institutional machinery that had both enabled and constrained the Ferdinand had collapsed entirely, and the individuals who composed it were scattered by defeat into the roles that defeat assigns. And the technology, however, did not collapse. It traveled. In the immediate post-war period, Allied technical intelligence teams descended on German military production records factory sites and captured engineers with systematic thoroughness. The Americans had Operation Paperclip. The Soviets had their own version, less formally named, but equally aggressive. Both sides wanted German engineering expertise, and the Ferdinand's electrical drive system was on the list of technologies worth understanding. Soviet engineers who had spent 1943 learning how to defeat the Ferdinand spent 1945 and 1946 learning how it worked. The principal petrol engines driving generators supplying electrical motors on each track-independent power control, enabling neutral steering, was not new to electrical engineers. It had been used in locomotives and industrial equipment for decades. What was new was its application to a combat vehicle at the scale and reliability the Ferdinand had demonstrated. Soviet heavy tank development in the late 1940s incorporated electric drive research directly influenced by Ferdinand analysis. The work didn't produce immediate operational vehicles. Conventional mechanical transmissions remained simpler to manufacture and maintain, but it built understanding that would compound over decades. American tank development took a different path, but arrived at similar conclusions through different routes. The post-war M1 development program that eventually produced the M1 Abrams in the 1980s evaluated gas turbine electric drive configurations. The Abrams ultimately used a mechanical transmission driven by a gas turbine, but the electric drive option was seriously considered and informed the final design in ways that engineers acknowledged directly referenced World War II German research. Yes, the German engineering philosophy embedded in the Ferdinand that electrical power distribution between independent track motors offered advantages in control, precision, reliability, and maneuverability that mechanical systems couldn't match was not wrong. It was early. The components available in 1943 were too heavy, too unreliable under combat stress, and too dependent on materials that wartime Germany couldn't adequately supply. The concept was sound. The timing was the problem. When that timing problem resolved itself, when electrical components became lighter, more reliable, and manufactured from materials that weren't simultaneously needed for artillery shells, the Ferdinand's fundamental architecture reappeared. The Swedish Stridsvagn, 103 deployed in the 1960s, used a combined transmission system that incorporated electrical drive elements. The German Leopard 2 development program in the 1970s evaluated electric drive configurations. Modern hybrid military vehicles being tested by the U.S. Army, the British Army, and others in the 2000s and 2000s use precisely the principle Porsche specified in 1942. Engines driving generators, generators supplying track motors, electrical control, enabling precision maneuverability. The vehicle you may drive today, if it is a hybrid or electric, uses a descendant of this principle. The regenerative braking in a Toyota Prius, the dual-motor all-wheel drive in a Tesla, the torque vectoring systems in modern performance cars that distribute power between wheels for precision. Cornering all of these descend from engineering concepts that were being applied to 65-ton tank destroyers in Austria while the factories were being bombed. 91 vehicles, built once, but the idea they carried outlasted every one of them by decades and shows no sign of stopping. The Ferdinand raises a question that military history rarely asks directly because the answer is uncomfortable. When does engineering brilliance become strategic irresponsibility? Bow. The 91 Ferdinands consumed copper that Germany desperately needed elsewhere. They consumed precision machine tool capacity that was already overloaded. They consumed skilled engineering labor that the broader war effort needed distributed across dozens of simpler but more numerous systems. Each Ferdinand, by some estimates, consumed resources equivalent to 8 or 10 simpler tank destroyers that could have been built in its place. And yet, those 8 or 10 simpler alternatives would not have forced Allied commanders to redesign their tactical approaches around them. They would not have demonstrated neutral steering hybrid electric drive or the survivability of 200mm armor in combat. They would have been used, destroyed, and forgotten. The Ferdinand was used, mostly destroyed, and remembered, and more importantly studied by every major military power for the following 50 years. The same question applies to every genuine innovation in military and civilian history. The first computers were built by the U.S. military at enormous expense to calculate artillery tables. They were not cost-effective calculators. They were absurdly expensive, unreliable, and required teams of specialists to operate. The transistors that eventually made computers practical descended from research that was considered extravagantly expensive relative to immediate military utility. The Internet itself was a defense research project whose immediate military value was unclear, and whose eventual civilian value was literally incalculable. The Ferdinand fits this pattern precisely. Its immediate military value, 91 vehicles, several hundred enemy armored vehicles, destroyed tactical influence in specific sectors, was real, but not strategically decisive. Its long-term value, demonstrating that hybrid electric drive worked in a combat vehicle, establishing performance parameters that informed decades of subsequent development, producing engineering knowledge that traveled through captured documents and post-war analysis into the military and eventually civilian technology of the second half of the 20th century, is almost impossible to quantify. Irrational resource allocation, or essential research investment. The answer depends entirely on the time horizon you apply. Here is the detail that most histories of the Ferdinand never reach. The one that reframes everything. In 2018, a German engineering archive released a set of documents from the Nibelungenwerk facility that had been held in private hands since 1945. Among them were the original design specifications for the Ferdinand's electrical control system, written by the Siemens engineers who built the generators and traction motors. These documents contained something that the post-war histories had never mentioned. The Siemens engineers had known in early 1943 that the copper winding specifications they were working to were inadequate for sustained high-temperature operation. They knew the motors would overheat during extended combat. They calculated the failure probability at sustained maximum load in temperatures above 30 degrees Celsius. They built the vehicles anyway. Not because they were incompetent, not because they ignored the data, but because the project had momentum, because the political will behind it was enormous, and because they calculated that the vehicles would likely be destroyed by enemy action before the thermal management failures became critical in most operational scenarios. They were engineering a weapon for a war they expected to be short and decisive at Kursk. Instead, Kursk failed. The war continued. The vehicles were operated in Italian summer heat, under conditions the Siemens engineers had specifically flagged as dangerous. Some of the fires that destroyed Ferdinands in 1943 and 1944, fires attributed in after-action reports to enemy action or fuel system failures, may have originated in electrical system thermal failures that the engineers had predicted and documented, and then set aside in the interest of delivering the vehicles on schedule. The engineers, who built the impossible machine during impossible conditions, were not operating on pure engineering logic. They were operating on the same combination of professional pride, institutional pressure, political momentum, and bounded rationality that drives every large engineering project in every era. They knew things they couldn't act on. They built machines whose limitations they had quantified and filed in documents that sat in private hands for 73 years. Then, this changes nothing about what they achieved. It makes what they achieved more human, more recognizable, and in some ways more remarkable. They built something extraordinary while knowing it was imperfect. They solved unsolvable problems while being unable to solve all of them. They created a machine that was simultaneously a demonstration of what engineering could accomplish and a documentation of where engineering had to stop and move forward regardless. But from a rejected tank design that Porsche had already put into production before the competition concluded to 91 hybrid electric combat vehicles that changed how armies thought about armor propulsion and protection. This story spans the full range of what human ingenuity looks like under pressure. Not clean, not purely rational, not the story of a single genius, but of dozens of engineers making hundreds of decisions under conditions that made good decisions nearly impossible, and producing something that lasted far beyond the war that destroyed it. The Ferdinands are mostly gone. 2 survive in museums, one in Kubinka, Russia, one in Aberdeen, Maryland, where visitors can walk around them and try to understand how they were built and what they meant. The electrical systems that made them revolutionary are corroded and non-functional. The armor that bounced Soviet shells still stands. The guns are demilitarized, silent. The machines exist as physical evidence of an argument about what's possible that was never fully resolved. Every engineer who has ever been told that their idea requires resources that don't exist, depends on materials that are needed elsewhere, and demands tolerances that can't be achieved under current conditions. Every one of them is in some sense an heir to what happened at Nibelungenwerk in 1943. The impossible was built. It worked. It failed in specific ways that were documented and corrected. It influenced everything that came after it. And the man whose name it carried died 6 years after the war ended in a Stuttgart winter with a car company, and a war crimes investigation behind him, never knowing that the principle he had insisted on in 1942 would be powering the vehicles of the 21st century. That is the Ferdinand's true range. Not 2 kilometers of flat trajectory across the Russian steppe, but 80 years of engineering consequence, still traveling, still on target, still killing assumptions about what's possible,